everything we've done here so far relies on the fact that the gas isn't doing any work. If the gas is doing work, then it's going to lose internal energy in order to do that work. So we want to see how it is that a gas can do work, and the answer is pretty simple. We think in terms of a gas in a cylinder. There's a piston so that the gas in the cylinder can expand or contract without any gas entering or escaping. So this cylinder, let's say, has a cross-sectional area A, and let's say that we keep constant pressure on this piston while the gas expands. Now, the only way that's going to happen, the only way the gas can expand with constant pressure is to heat it up, okay? And the molecules will hit the piston a little harder and cause it to recede so that the molecules have a greater space in which to move around, which reduces the number of collisions, balancing the pressure, again balancing the forces on the piston at the same pressure that we started with. Okay, so constant pressure P exerts a constant downward force P times A. So if we're going to expand this gas, we've got to exert a force P times A in this direction. Now, change the volume by delta V. How far does the piston have to move? This should be a fairly obvious answer. It's got to move a distance delta V over A. Since the volume of the cylinder is equal to the cross-sectional area times its times this dimension, call it the height or the altitude, then it turns out that the altitude is the volume divided by the area, so a change in altitude is going to be equal to the change of volume by the change divided by the change in area. Follows then that the work done is force times displacement. The displacement is delta V over A. The force is P times A, and we see that the work done is equal to P delta V. Now we can generalize this. Anytime a gas changes volume against pressure, some external pressure, it has to do this much work, regardless of whether it's in a cylinder or, say, an expanding balloon. In any case, the gas has to do this much work. It's P delta V. Now, if the pressure is not constant, then the work done is going to be the sum of it's going to be approximately equal to the sum of the work contributions from a larger number of delta V's, each of which is small enough that it doesn't cause much change in pressure. So when we sum up the P delta V contributions, as we change the pressure from this to that, and the volume accordingly, the sum of those contributions approaches the integral of P with respect to V, integral from V1 to V2 of P dV. And I didn't mention this in class because we were a little pressed for time, but of course that integral can just be visualized as the area between the two volumes. Let's call this V1 and this V2 beneath a graph of pressure versus volume. Okay, well, in any case, for the constant pressure case, P delta V being the work, we note that P delta V is just nR delta T. Since PV equals nRT, if we have a change delta T, then the nR delta T is going to be equal to the P delta V, and that's very straightforward. The work required, which is the P delta V, is supplied by the heat that we contribute to the system. So that in heating a gas at constant pressure, we do have to increase the internal energy. If it's a monatomic gas, the internal energy has to increase by nR delta T. And if it's a diatomic, if it's a monatomic gas, it has to increase by 3/2 nR delta T, diatomic gas by 5/2 nR delta T, just to speed up the molecules. If in the process the gas also has to do work by expanding, then we have to add another nR delta T. And this leads to the formulas that we saw somewhat earlier, a week or two ago, for the amount of energy you have to add to a gas, whether it be monatomic or diatomic, whether you're doing it at constant volume, in which case there's no work done, or at constant pressure, in which case you have this work done.